Right. So right up to this point, we have fit with the assumption that our uncertainties are Gaussian. So our parameters, the inferred parameters, are independent. They don't know enough about each other to really influence each other. The uncertainties in them, the distribution of that is Gaussian enough. So that's something that's the fit. That's our fit assumptions. These are things that we're, on the whole, we're fine with. Nope, can we switch this on? Yes. So we did bootstrapping, jackknifing. We had testing for these things. Like, well, what fit to use? We talked about, oh my gosh, is this now empty? Yes, yes, it is. OK, well, I'll just use hand gestures and whacking the keyboard. So what happens if our data is now non-Gaussian? There is a tail going one way, or there is a minority of values. This is no longer a neat, bell curve. Bell curves are so universally applicable that sometimes we just forget that they're not universally applicable. But we tend to use them anyway. And so what we're now learning, especially with big data, for example, that there is something that looks Gaussian, but then there's like a long tail. If you start looking at large numbers, the distributions aren't quite Gaussian anymore, and that's the part where it gets interesting. So we need something that is the function that describes where the values actually end for most of our fits, but it isn't a Gaussian that has these tails. And we call that the posterior probability distribution, or the probability distribution function. But that's abbreviated as PDF, which is really confusing in my, so that's to talked about. It's spooky season, so how do we do this? We used bootstrapping and jackknifing, but both of those sort of assume intrinsically that the inferred parameters that we get out of them are completely independent, and that the distribution we get out is OK to be Gaussian. That was the central limit theorem. But that doesn't mean that we always end up with one. So we had the what fit to use. And so, yes, we have good Gaussian errors. Then we can do a chi-square fit. These assume symmetric on both sides errors, not like one that looks like this, for example. And so if there are nuisance parameters, so essentially your model may need some extra variability, or there are some other shenanigans, really what you then get is a maximum likelihood fit. And then if you want errors on that, you'd use MCMC. So I want to talk about MCMC today. There is how you use it, what that looks like. It's not necessarily something that I expect you to be completely fluent in at the end, but we are using this way more in science, partly because we're starting to realize that various variables are weakly degenerate, so they're weakly dependent on each other, and we do want to know about that. OK, so this is Gaussian noise, and as soon as you get beyond that, you sort of need something else. Not Gaussian does not mean not random. Like they're quite. I know if you never tell me the odds, you have to quote Star Wars at some point in your life as a professor here. So these are, they can be, for example, we have known values, we have known unknowns. That's our model, that's the inferred data. And there might be an unknown unknown just lurking underneath there. There's something that sort of skews your data results, for example, very subtly. And so here's where you quote Rumsfeld, because he actually said the unknown unknowns, and that was the thing that he got very roundly mocked for. But honestly, you do have unknown unknowns. There's a thing you don't know, and that's usually the worst part of your model, like the thing that starts to mess with you the most. You have known knowns, things we are aware of and understand. So that's data and constants. We know those, right? That's the information. Model parameters are known unknowns. These are the things we're trying to infer. We have unknown knowns, so things we understand but we're not aware of. So, for example, biases, especially cognitive biases, sort of squarely, everyone knows. This is how I sort of start that one. Like, a bloke in the pub told me. Yeah, no verification. Everyone knows. This is where the biases stick. We know this. Actually, we don't. And The unknown unknowns, things that we are neither aware of nor we understand. That's funny, right? Often there's something interesting there, but it also happens to mean that your model gets messed up by unknown unknowns. So, Monte Carlo of Markov chains. Gaussian error is an assumption, easily leading to a small bias. So how to explore multidimensional parameter space effectively. How to spot degeneracies. How to compare multiple models with each other, especially if models are degenerate. How to compare completely different measurements to the same values. So suppose I have one lab setup and another lab setup, and both are measuring the gravitational constant, for example. How, if their uncertainties are not neatly Gaussian and symmetric, do I compare them? Yeah? Okay. Priors. So what goes in? A part of a parameter space to sample. We build in priors. We did this, right? We said, like, hey, if we have a slope and an intercept, this needs to be here. This needs to be positive, for example. You set priors, or something sets priors for you. And so you avoid physical parameters, temperature below 0 Kelvin, gravitational constants of 20, that kind of thing. Like you go like, yeah, I can't go all the way there. Warning, it's very easy to build in an unconscious bias at this stage. Remember that unknown knowns, this is the part where you accidentally put those in. Where you go, can't be less than that. Oh, it can be, oh, okay. Right, so then this is the part where you have to be very careful about that. Now what you then do, so we have a slope and an intercept again. And we have that, the chi-square field, the chi-square map, where we map how high that is. So we put a walker in there. And this is basically a little independent program that instead of just going, I am stepping through every possible combination of slope and intercept and just, linearly just brute force go through all of them. I've actually been told, and I was referring to this earlier, it actually has a couple of rules how it wanders through chi-square land, right? So it starts walking around pretty randomly, but turning around when the high values of chi-square get too high. Okay. So jump around crazily. And if you look at intercept or slope, this looks like complete noise, right? But it has rules in this chi-square map where it goes, I'm going out here. It's like it's sampling where since that noise reminded me of skating. So think of this as a skateboarder, right? It goes into the pipe and like tries to be as low as like, oh, it goes back up. Nah, I'm going to turn around. And as soon as I go back out of the pipe, so it's actually, this is sort of the shape of the skate park. But it spends most of its time in this area. That means that's where the solution sits. This is where the better solutions are. It doesn't spend a lot of time out here on either side. Why not? Those are bad solutions anyway. But there's a random value here. There's a randomizing. So if there happens to be a little part of the skate part where it does go down, it can spend some time there, which means that there are decent solutions off in a corner. All right, I have to put in a zombie reference here. Walkers, right? It's the Walking Dead, that kind of thing. Random walkers are pretended to be zombies that follow some rules. There are many different flavors of walker. This is one of the more fun like subtleties for these things. Like, what kind of rules do you give? What rules are actually the best at mapping this thing out efficiently, right? So random enough to probe the space. You do actually have to kind of randomly probe around. You do have to make a jump once in a while in order to make sure that you got the other dips in the chi-square space. But rules to ensure good coverage near the optimal value. So you need it's a balance of these two things. Because if I just optimize and there's like a little divot somewhere, I'll just fall into that little divot and that's it. I'll never get out of that local minimum. And I'll never find the actual good solution over there. So I need to be a little random. But I also need to cover the parts of the space that are interesting. So good rules for that. So it doesn't matter where you start, right? You start here and goes, nope, bad chi-squared. And it just does a random walk, and it finds a little minimum here for a bit because, yeah, it's not great. Like, it actually randomizes back out. Nope, nope, nope. Oh, look here. Oh, look here. And then it spends most of its time here. But this is the time spent. Hey, look. This is the distribution for good fits. This is the posterior distribution, right? So this is where good fits live. A little bit here, but actually most of them are here. So where this guy is sort of maps out in one of the parameters where the good fits lie. And it doesn't have to be symmetric. This can be any wonky shape. So especially if these are two parameters from many parameters, then you end up with these kind of donut, well, not donut, but like kidney-shaped things or even weirder. It helps identify these little islands. Like, it spends a little bit of time here, but it doesn't actually show. It shows up as a slight tail. But it spends some time here. This is a local minima. These are sort of okay models. The chi-square is a little lower, right? The higher, the more purpley the value is, the lower the chi-square. High chi-squared values, low chi-squared values. But there's a little low island here, and so I can actually learn about that. Okay, can I just pump my error bars and call it a day? Just make it like, the error bar is asymmetric. It's, here, I'll just use the big one, and that's fine. No, it's asymmetric. Overestimating one error, lower limit, and potentially still underestimating another, the upper limit. So this is not the way to do it. So if you do this, and now we do something that's called a corner plot. So a corner plot is every possible parameter for my model against every other possible parameter of my model. You look amused, or has nothing to do with the class. That's fine. All right. So what you get is that you have the red and you have the black measurements from two models, basically. Two models from two different measurement sets. And so I do a fit for the same parameters on two completely different experiments. So you can see that, hey, they both constrain H and DM. Don't worry what they are. Two different model parameters pretty well. They overlap okay. They agree. But they're a little degenerate still. Others, like here, is 100 omega. This is all cosmology. The red model does not constrain. The black model constrains very tightly. See how that works? So if I look at this, like there's no, and so if I just collapse it here, these values for H, they're all sort of allowed. But if I look at something like this value, there's like one value allowed by one of the models, and the other one is pretty much leaving it free. So I can immediately compare where they're degenerate, where they agree, the models, both of them agree, because like the contours overlap, or where one of them is really constraining and the other one is not. See, so I can actually take a multidimensional models, you fit to completely different data sets, and see how well those two agree. It's a good visual intercomparison. So does this have anything to do with Bayesian statistics? Yes. This is a XKCD, so it really like you have, and then you say, okay, I'm going to take another measurement based on what I know. That's what the walker does. I am here, the fit is terrible, I should take a step in a random direction. I am here, the fit is better than it was before, keep going, or at least have a high probability of keeping going. So that sort of takes my previous experiences into account. That's really the Bayesian part of this. Okay, so these histograms for each of these parameters are the posterior probability. Like this is for this particular, for DM, I get this posterior. That's a pretty good Gaussian. This is a Gaussian, that's a Gaussian. That's fine, this is a Gaussian. The red line isn't a Gaussian. So you can tell, like if I do the best fit for this one, that's like here, and the uncertainty is like this big, this big this way, and huge that way. So I get an asymmetric one for the red model for 10 to the 5 omega r naught h squared, whatever that is. That's a mouthful. I'm just calling that one Bob, right? So that's my model parameter Bob, and Bob is poorly constrained by red, but perfectly well constrained by black. But I can get a symmetric error bar from one model and not from the other, and I can compare them then. So those are the posterior probability distributions. So it is also a better link to scientific vocabulary because, remember what we did here? This was 1 sigma, this is 2 sigma, this is 3 sigma in the Gaussian distribution, right? So a 5 sigma result is, 3 sigma result is like, that is significant. However, you can also say, here's my confidence interval. The value lies within this range. This is the best value I got, the most common one. More accurate statement and say, this is the standard deviation, so the Gaussian distribution, and say, hey, this is where it ends up. This is a joke. But honestly, as an immigrant here, I can tell you that it really feels pretty accurate. So objective, it's got pretty good in the middle. Americans, things are starting to sound like, people say awesome well before you get to the top of things. And Eastern Europeans are like, it's very negative folk. And this is not, depends a little bit. I sort of hover in the middle there. Okay, so you can do these distributions. So let's take a real-world example of MCMC. So something that I did with my students. Model can be complex and degenerate. Even the simplest one, fit the line, actually has a bit of degeneracy in it, right? It's never a nice round. If it's nice of round distribution, that means one doesn't know about the other. It's just a random distribution around the center. So if you have some like banana-shaped things or elongated things, that's degenerate. So data is sparse but covered the desired parameter space. So maybe you have something that is weirdly distributed, maybe not fully covers the area that does fully cover it, but there might be some unknown unknowns. And so fit the entire Milky Way shape from 274 star counts. So we have the positions of 274 stars. Pretty okay. Like, we have a decent measurement-ish. But they are randomly sampled on the sky. We don't have like a neat uniform coverage. So this is what the idea was. You have a Hubble picture, and Hubble picture is tiny. If you put let's see, George Washington is on the quarter, right? Yeah, you put a quarter at arm's length. George Washington's eye is the coverage of Hubble on the sky. That's how big Hubble, how big a chunk of the night sky Hubble actually takes a picture of. So that's tiny. So you get this whole thing is literally in George Washington's eye, and then you go like, oh, look, there's 1 star, 2 star, 3 star, 4, 5, 6, 7, 8? I think that's it. So I have a few stars, just a few stars in every Hubble picture, because again, the Milky Way spans the entire sky. I'm just looking at a tiny bit of it. I'm sampling very randomly throughout. So instead of all of the Milky Way, I'm taking little bites, little plumbing depths. So I realize not everybody's very nautical here in Kentucky, but if you want to, for example, figure out how deep the harbor is, you putter around a little boat, you have a lead weight with a line on it, and you just drop it. Drop it, hit the bottom. It's this deep here. Put, drop it again. Put, drop it again. Right? So you get this random sampling of basically this drunken boat ride through the harbor trying to figure out how deep everything is. And then you try to map it out. So you sort of do the same thing here. You drop a line through the Milky Way and count stars. And as you can see from the axis here, it goes to about 5 per square arc minute. Like, that's really, it's 9 square arc minutes per Hubble picture, so that's, 5 times 3, so 15 was the highest count we got. So it's low count numbers. But then we have a model. We have a model where it says this is the density as a function of, so the Milky Way is a disk, so we have a radial, and then above the disk is z. So that's the height above the disk. So cylindrical coordinates. See, 1 knot, 2 knot, cylindrical coordinates this is what cylindrical coordinates are. Radius in the xy plane, you have a radius, and then above the plane, you have height, z. Okay, so that's our coordinate system. And we say, all right, we have a central density, r naught. We have an exponential drop-off with radius, and that h is the scale height for that. And then we have a function called sec h squared, which is the secants, which is the inverse sine, I want to say. Anyway, and we square it. Sec h is a function in Python. We never thought, we looked it up once, and then it was like, yeah, that looks right, and then moved on. And this is the height of the disk with another scale. And then we have a second component, which is spherical, basically a fraction of that central position. This is the position at the sun. But then the radius, the scale height, and then we have another parameter. Hey, I should probably model that. So I have data. I have positions of these stars, right? I have the radial, and if I know the distance of these stars, I have a r and a z for each star. I can map that out. I have knowns, so this is the radius of our sun. This is the height of our sun above the plane. This is the density of the stars at our sun. We know that the best because that's where we are. Okay, so we have a couple of knowns. Cool. We have data, and we have unknowns. These are our model parameters. That's 1, 2, 3, 4, 5, 6 parameters for a simple two-component smooth distribution of the Milky Way. This is literally a disk that declines with the radius. And this one is a spheroid with a certain decline with radius as well. Okay, this is what you do. You do this MC thing where you run around with a whole bunch of walkers and see what the best fit is. And so you end up with things like, yeah, this is pretty Gaussian. These two things don't know about each other. This is great. This one's fine, this one's fine, this one's fine, this is fine, fine. These two are degenerate. Okay, so this one, FH with P and rho naught with P, rho naught with, but this is a nuisance parameter, so never mind. So we get pretty good error bars. We get, most of them are fairly Gaussian, some of them are not, right? This is a little skewed. It's good to know. This is actually also a little too tight. So you get slightly different distributions. So we can actually say things like, hey, this is the best fit, and this is our confidence interval. This is the best fit, and here's our confidence interval. We're confident on the low end, but we're not so confident on the high end. For example, our data constrains the low end better than the high end. It is a more accurate description of what we're actually looking at. So this is why I like MC models. Sorry, I thought we had a summary. The neat thing was that this was their undergrad bachelor thesis, the two of them. So I just like, okay, here's my catalog, go fit this model. And honestly, this is the funnest part for a professor ever. They go like, okay, and just ran with it. They went like, oh yeah, we found a better walker. I was like, I didn't know there were options. Right? They ran ahead of me very, very quickly. But they constrained Z naught, P, the K, like the oblateness of the halo. They modeled this perfectly. And not only that, we got uncertainties on all of them that we could compare to how other people had found these. So yes, that is the monthly notices of the Royal Astronomical Society 2016. Right? They basically handed in their thesis. I was like, that's cool. Can I turn it into a paper? And they said, fine. And I stripped out the reference to Wikipedia, and I was pretty much done. So that was a fun exercise. Now, the thing is, you can do these model comparison. You can do multiple parameter models, non-Gaussian uncertainties. Really important because you can say, like, hey, we're good on this side of the value, but not on the other. The nuisance or random parameter. So if you have something that is a model parameter, you can see how well that constrains. You can check for degeneracies, and how to compare the model to model. Different parameters left free or with a very strict prior. You go like, hey, guess what? I think, you know what? Somebody else has measured the scale height length for the disk. Like, let's fix this to a value that somebody reported. Let's fix this one to a value somebody reported. Or let's fix this one. So pick one and actually fix some of these parameters that way and see how A compares to B, model A compares to. Now, remember the reduced chi-squared? If like you take the chi-squared and divide it by the number of free parameters, right? Number of free parameters, 1, 2, 3, 4, 5, 6. So I could do a chi-squared for the whole model and divide by 6, and then take a different model where I fixed one of these, say like this one, so it's 5, and divide that by 5, and say, look, that model's better than this one. But I can also do the visual thing where it's like, okay, I can compare this one to the one with the 5 parameters and see how neatly it looks. So I take just the disk, for example, just the top part of the model. I fix it like I don't use the rest. Well, my walkers do not spend a lot of time in the center. They sort of randomly rattle about and never quite settle on a point. It looks like it's a good description, but look at the other one. They spend way more time in the center. If I do a disk plus halo, that's what I just showed, like everything is much more constrained, right? It's much tighter in the center. If I fix one of them, that's actually not so bad, but I'm getting some weird stuff happening here, and suddenly this is degenerate. So fixing the fraction of halo wasn't something that helped. Fixing the scale length wasn't so bad. Look, that does a pretty good job. Whatever we put in there, we can't constrain this one very well, and if we fix it at the value that we have, we get a pretty good model. I fix P. Once again, something goes wonky here, and I'm not so sure, like, we introduced 2 degeneracies. So you can sort of estimate, like, if I start seeing neat little round results, that's the better model. I can visually compare the models immediately. I'm a very visual person, but also you can look at these posterior distribution and go like, whew, something's really off here. And if I say I fix R naught, I say like, well, let's know we know what the density of stars is in the center of our Milky Way. Absolutely not, right? We gotta leave that free. So you can literally say this one looks uglier than the other, and that's a good visual estimate. It's better than the reduced chi-squared. It sort of has all the information in there. Now I want to note here that this is the fraction of stars in the halo, the stellar halo, the blob of that second part of the model. That's FH, and we get one that is 7%, I think. Yeah, 7% of the stars are in the Milky Way halo. We go to 11%, and it goes down to almost 0, like 0.1%. So it's an asymmetric. This is on a log plot. It is an asymmetric error. So you can have an asymmetric error on a log plot. It's way bigger, right? This is in steps of 10. And so it tells you, hey, we're actually constraining it up here better than we are constraining it down here. And we can compare to, drum roll please, 1, 2, 3, 4 other models that we have for other galaxies. So we didn't have a lot of these. We can compare it directly to the Courteau value from 2011. So, hey, we actually agree pretty okay. This is only a little bit lower, but we get a slightly higher value from that. If you integrate out about the whole thing, remember we started with 274 stars of a particular kind, and you say, okay, here's my model. The Milky Way is this big. The halo is this big. We end up with 58 billion of them, inferred from 274, because we constrained our model with the 274 and said, okay, well, we only get really small part of the Milky Way. What do we then? What's the total? So yay, that goes to that gets news. It goes into the news. So that was a really fun project for me. But this is the kind of thing where why do I introduce MCMC? Because having these random walkers, if people start talking about Bayesian statistics, honestly, it is really going, hey, our probability function isn't particularly Gaussian. In the real world, because of degeneracies, because of unknown unknowns, you get a non-Gaussian distribution of the posterior, the likelihood where you end up. So that's why we do this with lots and lots of walkers. And I want to I forgot to mention one thing here. Now, this is a little computer program. I've literally sent this little computer program. This is one walker, and like go into this parameter space, calculate the chi-squared, and then do what your programming tells you to, and then look where it spends its time. So remember that chi-squared trough that we have a slope and intercept, right? There was a, here it is, so that's exactly what this is doing. Of course, that's a little computer program. If I have a cluster or a modern desktop machine even, they have, you've seen like, here's the latest desktop, it has 8 cores or something like that. These really heavy duty desktops. Blink, blink. Does everybody, does any of you actually have a desktop machine? Okay. Right. So some of the later versions of the Macs and et cetera that are for like really heavy duty graphics stuff or really heavy duty rendering stuff, they have multiple processors. Instead of adding more computing power to the one chip, they have basically said this motherboard has 8 processors or what have you. The larger computers essentially are, this is just a bank of processors, so they have like 20 cores. I can give each of those cores one of these things to do. Or I can just run multiple of these programs. These are completely independent of each other. So I can have one walker map this out, and then I basically go, throw a second walker. Throw a whole horde of these zombies at the problem, right? So before you know it, you have 4,000, 5,000 of these walkers just bouncing around in here, mapping out where they spend most of their time, mapping out your chi-square space. So that's the trick behind MC, the Monte Carlo Markov chain. Monte Carlo comes from Monte Carlo. Who has heard of Monte Carlo? Okay. Who has seen, I think it's the second of the Iron Man movies with the racing, right? That is in Monte Carlo. The Monte Carlo Formula One race is the hardest and most dangerous race because it's going through a little Italian town, or complete independent municipality in the southern French coast that has a lot of gambling going on. So Monte Carlo is a gambling strategy, which is, I'm not going to try it once, I'm going to try it loads of times. It's essentially saying, I'll win against, it's how the house wins, right? The house not necessarily wins every time, but the house wins eventually. I'm trying to convince you to never gamble because the house always wins. You try every time, and if the odds are enough in your favor, over enough gambles, you'll win. So if you're betting against the house, you're hoping that you're in the tail end. Okay, Monte Carlo is a technique where you go, okay, I know what the rules are, and this little walker knows what the rules are. I'll just do it loads of times, and then I know what the posterior, what the odds are. That's how I get the odds. So I could do this with one walker, and the Markov chain part is like, if you do a roulette wheel or something like that, you just go, the last time you ran the roulette wheel doesn't know about the current roulette thing doesn't know about the last time you ran it. This one does. This is the chain part. Like, I knew where I was here, and the rules told me to go this way. So that's the chain part. Like, they're all linked together for each walker. So do it loads of times, Monte Carlo, and then have a couple of rules so that you don't spend a lot of time wasting your time on poor fits. So between those two things, MCMC is a very powerful way of mapping out the chi-square space for any model and with any kind of data. So if you have sparse data, like we did with the Milky Way, or you have a very complex model, like we did with the Milky Way, or you have a model that you don't know exactly which one of the parameters are the most important, so you want to switch one off or fix one once in a while, or you have two completely different data sets, like that we had with this one. Completely different data sets with trying to measure the same parameters, and you want to compare them. So suppose I am group A, I have the red team and I have the black team here. And red team and black team want to produce a paper together saying, hey, we constrain these values when we combine information. When I do that, I get a fantastic value for this one from the black team. That's great, grand. But if I then combine the values, for example, from these two, I get one that's here that has a better distribution. If I do this one, I go like, okay, red team doesn't constrain it, black team constrains it more, so I get I can convolve these two. Or I can do that visually, basically going, yeah, it's in here. Yes, it's in here. The black team, or with this one, yeah, we don't constrain that much more. So it gets really interesting in science when these two ovals, for example, don't overlap at all. That's when we have a problem, right? Because now the 95% confidence intervals for both things, for both measurements, are completely separate. There's daylight between them, which means we're either in the 5% odds that this was a happenstance, or someone's model is off. Right? That's where we're at with the Hubble tension right now. So there is a moment where you go like, hey, these two blobs are no longer overlapping. So this is the kind of thing that you can do with MCMC. You can actually map these shapes out properly and then compare them. Any questions about why we would use MCMC and what you would use it for? So would you use this for a slope-intercept fit? Or is it a little overkill? It's a little overkill. Can, but it's overkill. But as soon as you have something that has 9 parameters, for example, would you do that? Yes, that is. I don't know where the degenerates sit. I don't know which one of these parameters is actually really poorly constrained versus really well constrained. So I can actually map that out. And that's what this is so useful for. I don't necessarily know. If I knew the answer, it wouldn't be called research. Right? Paraphrasing Einstein a little bit, is like, but if we knew what we were doing, this wouldn't be called research. If we knew what the parameter was that we are actually constraining with our data, it wouldn't be called research. Maybe we accidentally do another one much better than the ones that we thought of. So you sort of go in blindly and go, here's our model, which ones can we constrain the best? And then you end up with what it turns out you can constrain the best. So that's why we use the Monte Carlo. That's the Monte Carlo part. The Markov chain is the fact that it knows from the one. Like it's sort of like rolling the dice as if the dice remembers where it was last. Like, does that make sense? And then just keep doing it, right? Where does it end up most of the time? You can have a fun experiment like flip a coin, right? Flip a coin, flip a coin, flip a coin. Eventually, you should get equal numbers unless it's a weighted coin. So this is how you figure out if it's a weighted coin or not, or a weighted die or something like that. That's doing the Monte Carlo way. But if it knows about its previous ones, then it's a Markov chain. Okay, and then figure out the non-Gaussian part and get the posterior. See, this is my 16 to 84% range of possibility. Like my data sits in here. So you can actually say that this is the most common value, but it sits in this range. So you can have an asymmetric error. Yeah? So that's where asymmetric errors come from. Because sometimes you'll see those. You'll have like upper limit, lower limit. And they're not symmetric because they did this. Okay, this is an important thing. Like this is how we go. Like everything I've taught up so far is what we've been doing mostly until, let's say, the 1980s or 90s. So science usually assumed it was a Gaussian uncertainty, did the fit, did the linear regression, was like, okay, and here's the uncertainties based on the chi-squared, based on the linear model. Maybe some bootstrapping, but that was it. But then we realized that actually there's real models and real life is a little more complex, so this is how we capture that complexity. Yep. All right. Cool. Well, that was what I wanted to tell you, everyone. So I'll stop the recording. Let's hope we have voice time this time.